Okay, hello everyone. In this video, I'll be going through the chapter of further differentiation, looking at how do we differentiate exponential and logarithmic functions. So this exponential logarithmic function should have been what you have learned in Sec 3 A Math. So in Sec 4, we are going to learn how do we differentiate any functions containing these, whether we have exponential terms or logarithmic terms. Okay, so let's begin. I'll start by recapping what we have learned in Sec 3A Math. So if we remember from the exponential functions and logarithmic functions chapter, we learned exponential functions. How do we draw the graph of exponential functions? So we learned that the graph of y equals to e power x. This is an exponential function whereby the power or the exponent is, in this case, x, which is an unknown or a variable. So over here, if I were to plot this graph, you remember from Sec 3 A Math that the graph of this y equals e power x looks something like this. So let's look at the result. The result is that if we were to differentiate any function, any exponential function containing e power x, I'll get back e power x. So how do we understand why is this like that? If we recall again, what we have learnt in this chapter of derivative, what does derivative mean? It basically means the gradient function. So when we want to find the derivative of a function, we are actually finding the gradient function. What is the gradient of the curve at different points along your x-axis for different x values? So in order to give you a quick understanding, similar to how we differentiate trivial functions, we always look at the graph to see how do we obtain the gradient function of this graph over here. How does the gradient change along with based on your graph over here? So I'm going to show you a short YouTube video to explain this for exponential functions.
Let's consider the function f of x equals e to the x and plot it on the axis here. We can draw the tangent line to the curve, which looks like the curve locally, and whose slope is the instant rate of change of the curve. We can compute the slope of this line, and we see that here it's 0.08. As we move the point along the curve, we see that the slopes of the tangent lines get larger. In fact, something even more interesting happens in this example. If we also plot the y-coordinate of the point, we see that as the point moves along the curve, the slope of the tangent line actually equals the y value. We can take this one step further, where we plot a new graph on a new set of axes. Here the y value will be the slope of the tangent line from the first graph. As we move the point along the curve, we map out this graph. The function f of x equals e to the x is a special function because its derivative, or its slope function f prime of x, is also e to the x.
Okay, so I hope this video here tells you that if we were to analyze the gradient function of this graph over here, we know that the gradient is exactly equals to the y value for each of the different x value, which is why we have the result over here. When I differentiate any exponential function e power x, I will get back e power x by itself. Okay, so this is one very important result which you will need to know as we continue to differentiate different kinds of function. So let's look at example 1. Example 1, differentiate the following with respect to x. Let's look at 1a. Okay, I'm supposed to differentiate, remember presentation, differentiate x plus 1 times e power x. So over here by my product rule, I have two terms that is multiplied to each other. By product rule, I can differentiate this by differentiating the first thing here first, which will give me 1 times e power x, then plus, now I keep this first term, I differentiate the second term. So I keep x plus 1, and if I differentiate e power x, I'll get back e power x. Okay, so therefore my final answer is simply e power x plus, over here I have e power x times x plus 1. I can actually simplify further by factorization. Factorize out e power x from both terms. I'll get 1 plus x plus 1. Therefore, final answer is simply e power x times x plus 2. Okay, this is for example 1a. Okay, let's look at example 1b now. Okay, for example 1b, I have this fraction over here. Okay, I'm supposed to differentiate 2e power x over x. Okay, so how do I differentiate this? Now I have a fraction. I have the variable here in the numerator and denominator. So I can apply the quotient rule. Quotient rule means differentiate the numerator first. So I'll get differentiate numerator. So this is 2e power x. If I differentiate 2e power x, This e power x differentiate will get back itself, so it simply equals to, I'll get back 2e power x times the denominator x minus away, now keep the numerator, 2e power x, then differentiate the denominator, which is 1, the whole thing divided by the denominator square, which is x squared. So if I were to simplify this, I'll get 2x e power x minus 2e power x over x squared. Okay, then from here I can simplify this further. From here, I can factorize out the e power x from the numerator terms. I'll get e power x times 2x minus 2 over x squared. And I can actually further factorize out a 2 over here. I'll get 2e power x, x minus 1 over x squared. Okay, this is for example 1b. Okay. So very simply, if you know how to, if you can apply this rule here, we can now start to differentiate different terms with exponential functions. Let's move on to example 2 now. Okay, but before that, we need to learn this new thing called the chain rule. So let's say, right, in this exponential function, instead of x, I have a u over here, and this u contains terms that is not just x. In order to differentiate this exponent, I will keep this exponent e power whatever u over here, times differentiate the power. So let's illustrate this using an example. Let's look at example 2. Example 2a. I want to differentiate with respect to x, e power 2x plus 1. So how do I differentiate this? Okay, I know that now my power here is not just x but 2x plus 1. Using the chain rule, it means I'll keep this thing over here, keep this original thing. This will be equals to e power 2x plus 1. Then now I'll multiply this by differentiating the power. Differentiate 2x plus 1 will give me 2. Okay, and now my final answer is simply 2e power 2x plus 1. This is for example 2a. Okay, let's look at example 2b now. Part b. If I want to differentiate I have square root x, I can rewrite square root x to become x power half. Okay, so therefore if I want to differentiate this, same steps. Now instead of a x here, I have a x power half. So I keep this same thing here first, x power half. Then now I'll multiply this by differentiating the power. Differentiate x power half will give me half times x power negative half. Okay, this is by the power rule. Okay, then from here, I simplify this from here. I will get e power x power half times, I turn this into a positive index. This will be times 1 over 2x power half. Okay, so therefore, final answer, if I simplify everything, I'll have e, instead of half, I can bring back the square root now. This will be e power square root x over 2 square root x. And this is for example 2b. Okay. Alright, so now let's look at example 2c. For example 2c, I want to differentiate this. Okay, so let's write it out. Differentiate e power x minus 1, the whole thing power 5. Okay, so in order to differentiate this, you recall again, we learned this in chapter 12. In order to differentiate anything with a big power, this is your chain rule as well. I might bring down the power, this current power minus 1. Then after that, I times differentiate whatever that's inside the bracket. So the steps are the same. So I bring down the power 5. The current power minus 1 will be 4. Then now I multiply this by differentiating what's inside the bracket. So differentiate e power x will give me e power x again. But differentiate the constant negative 1 will be 0. So this is simply times e power x. Simplify everything from here. Final answer is simply 5e power x times e power x minus 1, the whole thing power 4. Okay, this is for example 2c. Okay. Then now the last one, for example 2d. Okay, I want to differentiate this. I'm differentiating. Now it's e power x, the whole thing power half. E power x, maybe instead of the square root, I'll change that to e power half. Okay, and you can notice by your laws of indices, we can combine these two together. Okay, I'm differentiating essentially e power x over 2. Okay, I hope you still remember how to apply your laws of indices. Then from here, recall to differentiate this again. Okay, over here it's not just x but x over 2. So how to differentiate exponents? I keep this the same thing over here, e power x over 2. Now I multiply this by differentiating this power. So differentiate x over 2, I'll get half. Okay, so therefore my final answer is simply half e power x over 2. Okay, or you can also rewrite this to become, let's say, half e power x, the whole thing power half, and this can be seen as half of square root e power x. Okay, but I think stopping here is fine. This is equivalent to this expression here. Okay, and this is for example 2D. Okay, so we have finished example 1 and 2 on how to differentiate these basic functions containing exponents. Now let's look at example 3. Example 3, differentiate the following with respect to x. Okay, let's look at example 3a. Okay, you can try this by yourself if you want. You can just simply pause the video. I will continue over here. Example 3a, if I want to differentiate this fraction, okay, whenever I see square root, do not get confused, I will turn this square root into a power so that I can easily manipulate these different, instead of square root, I see a power half instead. So over here, I'll get e power x over 2 over 2x. Okay, so I want to differentiate this entire expression here. Okay, this is a fraction, contains x unknowns in variables in this numerator and denominator. That means I'll apply the quotient rule. So to apply my quotient rule, I'll differentiate the numerator first. Differentiate numerator, we recap again. How do we differentiate this? We actually done this in example 2D. Okay, differentiate this is keep e power x over 2 times half, differentiate the power, then this whole thing multiply by denominator 2x, then minus away. Now keep the numerator e power x over 2, then now differentiate the denominator, which is 2. Okay, the whole thing divided by the denominator square, which is 2x, the whole thing square. Simplify everything from here. Half times 2 will give me 1. So this will be simply x times e power x over 2 minus away 2 e power x over 2. This whole thing divided by 4x squared. Okay. Then you can therefore factorize out common factors from the common terms from the numerator. I have e power x over 2 as a common factor over here, so therefore I can factorize it out. E power x over 2 bracket x minus 2, the whole thing over 4x squared. Okay, and if you want to, you can also rewrite this to become square root e power x times x minus 2, the whole thing divided by 4x squared. Okay, and this is the answer for example 3a. Okay, so now let's look at example 3b. Example 3b, let's write out, I want to differentiate this expression over here. So let's, instead of square root here, I have square root x times e power cosine x. So I will rewrite my square root x to become x power half. So I'm differentiating x power half times e power cosine x. Okay, so this I can apply the product law. The product rule over here, first step, I will differentiate the first term first. So I'll get half x power negative half, keep the second term, times e power cosine x. Then now I will plus, now I'll keep the first term, x power half, then differentiate the second term here. So this is e power cosine x, so to differentiate this mean, I will keep e power cosine x, then now differentiate the power, which is differentiate cosine x, which will give me negative sine x. Okay, then from here I simplify it step by step. I will get over here this x whole negative half can be rewritten to 1 over 2 root x e power cosine x, then plus I have minus sine x. I can bring the minus in front, so this will be minus sine x, okay, times square root x e power cosine x. Okay, then I can further simplify this from here. Okay, by further simplification, I can factorize out my e power cosine x. Okay, so if I were to factorize it out, I will simply get e power cosine x times 1 over 2 root x minus, you can write the root x in front because this is sine x times square root x. So to not get confused, I can write square root x sine x. Okay, and this is the factorized form over here. If you want to, you can further simplify this, but it's not necessary. This would be the differentiated form for example 3b. Okay, and with that, we have completed the differentiation for exponential functions for this chapter. Okay, and you can go and try the practice questions now. You should be able to do them after watching this video. Okay, so now I'll just move on to the next part over here, differentiating logarithmic functions. So in order to give you a better example of that, I will show you another quick video to understand why when I differentiate ln x, I will get this expression here, 1 over x. Okay, so let me go to the short video now.
So in this video, we're going to think about what the derivative with respect to x of the natural log of x is. And I'm going to go straight to the punchline. It is equal to 1 over x. In a future video, I'm actually going to prove this. It's a little bit involved. But in this one, we're just going to appreciate that this seems like it is actually true. So right here is the graph of y is equal to the natural log of x. And just to feel good about the statement, let's take the slope, let's try to approximate what the slope of the tangent line is at different points. So let's say right over here, when x is equal to 1, what does the slope of the tangent line look like? Well, it looks like here, the slope looks like it is pretty close to being equal to 1, which is consistent with this statement. If x is equal to 1, 1 over 1 is still 1. And that seems like what we see right over there. What about when x is equal to 2? Well, this point right over here is the natural log of 2, but more interestingly, what's the slope here? Well, it looks like, let's see, if I try to draw a tangent line, the slope of the tangent line looks pretty close to 1/2. Well, once again, that is 1 over x. 1 over 2 is 1/2. Let's keep doing this. If I go right over here, when x is equal to 4, this point is 4 comma natural log of 4, but the slope of the tangent line here looks pretty close to 1/4. And if you accept this, it is exactly 1/4. And you could even go to values less than 1. Right over here, when x is equal to 1/2, 1 over 1/2, the slope should be 2. And it does indeed, let me do this in a slightly different color, it does indeed look like the slope is 2 over there. So once again, you take the derivative with respect to x of the natural log of x, it is 1 over x. And hopefully you get a sense that that is actually true here. In a future video, we'll actually prove it.
Okay, so I hope that as usual, you only learn how to prove by limits at A levels. So for this kind of functions, at O levels, we will use the graph to appreciate why. When I differentiate ln x, you notice that for the graph, if we saw in this video over here, the graph of y equals to ln x, okay, the gradient function follows the 1 over x, this expression here. So that is why when I differentiate ln x, I will get 1 over x. Okay, so let's use this result over here. How do I apply it now? Let's look at example 4a. Okay, example 4a. Differentiate the following with respect to x. Let's look at 4a. Okay, I remind you again, when I want to differentiate something and the question never state this, you cannot just write this is equal to whatever answer over here. Presentation wise, you should write, I want to differentiate this expression, so it should be I'm differentiating with respect to x plus 1 times ln x. Okay, this should be the correct presentation. Then you can now write the answer. Differentiating this expression will give me, by product rule, differentiate first term first. I'll get differentiate x plus 1 is 1. Keep ln x. Then now plus. Keep the first term, differentiate the second term. So keep first term is x plus 1. Then differentiate second term, differentiate ln x is 1 over x. Okay, so therefore final answer to this question is simply ln x plus 1 over x. This is for example 4a. Let's now look at example 4b. Okay, I want to differentiate now ln x over x. Okay, so what we can do is that simply this is a fraction. I have variables in my numerator and denominator, which means that I have to apply the quotient rule. So how do I apply my quotient rule? Differentiate numerator first. Differentiate ln x is 1 over x times denominator, which is x, minus away, keep the numerator ln x times differentiate the denominator, which is 1. Okay, then the whole thing divided by denominator square, which is x square. Simplify from here, I will get 1 over x times x will give me 1 minus away ln x over x square. Okay, and this is your final answer to example 4b. Okay. Alright, so let's look at example 5 now. You can try the examples first if you are confident. Not sure, you can watch my video. Okay. Next one here. Now, similar to exponential functions, instead of x, if now I have a u. Okay, the difference is that now, in order to differentiate any logarithmic functions, we focus on ln. I'll take note that, okay, I didn't mention this, but for O levels so far, we don't learn how to differentiate log. We focus on ln. Okay, ln x for now. Okay, so over here, let's say if I have ln u, how do I differentiate this? Is like same as ln x. If I differentiate ln x, I get 1 over x. So now if I want to differentiate ln u, I will get 1 over u, but now I'll multiply this by differentiating this u, similar to exponential functions. Okay, so if you are not sure, let's look at example 5 to illustrate this. Okay, example 5. Okay, differentiate the following function with respect to x. So I want to differentiate this over here. Let's write down the expression. Differentiating with respect to x, ln x squared plus 4. Okay, so in order to differentiate this, we follow the steps. Instead of x here, this becomes x squared plus 4. So I follow these steps over here. It will be 1 over x squared plus 4. But now I'll multiply this by differentiating whatever that's inside this bracket here. Differentiate x squared plus 4, I'll get 2x. Okay, so therefore final answer to this question is simply 2x over x squared plus 4. This is for example 5a. Okay, let's look at example 5b now. I want to differentiate with respect to x ln e power x plus 1. Okay, so we follow the same steps. I will get 1 over whatever that's inside this ln function here, which is e power x plus 1. Then now I'll multiply this by differentiating. Inside this ln function, which is e power x, I'll get e power x. Because differentiate e power x is itself, differentiate 1 is 0. Okay, so therefore final answer is simply e power x over e power x plus 1. Okay, and now for the last one, part C, I want to differentiate with respect to x ln 2 cosine x plus 5. Okay, so this will be equals to, same steps, 1 over 2 cosine x plus 5. Then I'll multiply this by differentiating what is inside the bracket over here. So you know differentiate 5 will be 0, but differentiate 2 cosine x. Recall that differentiating cosine x will give me negative sine x. So this will be equals to times negative 2 sine x. Okay, therefore my final answer is simply negative 2 sine x over 2 cosine x plus 5. Okay, and these are the solutions for example 5. Okay, so now you can try example 6 by yourself first. Okay, then you can pause the video. I will continue with example 6, the last examples for this worksheet. Okay, let's look at example 6 now. Differentiate these functions here. So now we have to start recalling what you have learned in Sec 3A Math. How do we use the laws of logarithm? Okay, so let's look at 6A. I'm supposed to differentiate d over dx ln e power x plus 1, the whole thing square. So you see that if you were to differentiate this directly, it will be 1 over this whole thing here times differentiate this whole thing. So you can actually use what you learned in Sec 3 A-Math to make your life easier. Let's use our power law to actually bring down this power here. This is equivalent to differentiating 2 ln e power x plus 1. Okay, and therefore this 2 is just a constant multiplied to this. So I'm just need to focus on differentiating this part over here. So this is simply equals to 2 times, now I differentiate this entire ln function, which is 1 over e power x plus 1 times, differentiate inside the bracket now, which is e power x. Okay, therefore final answer is simply 2e power x over e power x plus 1. Okay, this is for example 6a. Okay, let's look at example 6b now. Okay, 6b here I'm given that y is defined to be this ln function over here. So to differentiate this, I can now write simply dy over dx, since y is already defined to be this expression over here. Okay, and you see that inside here, this is a fraction. It becomes very hard to differentiate it becomes very troublesome if you were to use a quotient rule. So by what you learn from the law of logarithm, okay, we want to split this apart first. So maybe let's rewrite this term over here. Y can be rewritten as, okay, let me move this down first. Y can be rewritten as ln x squared sine x. Okay, we put a bracket to signify this ln applies to this function here. Then minus away ln x plus 1. Okay, remember you learned this last year. We can split ln functions with fractions inside. Okay, this whole thing over here is the same as this thing over here. Okay, then now what I can do is simply differentiate this term by term. Okay, before I write dy over dx, if you recall again what you've learned last year, this can be split further into ln x squared plus ln sine x. Okay, this is what you learned last year using a product law as well. Minus away ln x plus 1. Okay, let me make it clearer. So this one you can see that these two terms can combine to give you this using your laws of logarithm. And you can now further split this apart. This 2 here, we make your life easier. Anything with power is troublesome. This can be rewritten to 2 ln x plus ln sine x minus ln x plus 1. Okay, so therefore now that your y is now these 3 terms, you see this looks so much easier to differentiate compared to this original ln function here. And you are less prone to making careless mistakes. So therefore, from these things over here now, dy over dx, simply differentiate your first term here first. Differentiate 2 ln x will be simply 2 times 1 over x plus, now differentiate ln sine x, it's simply 1 over sine x times differentiate sine x, which is cosine x. Okay, then now the last one, differentiate negative ln x plus 1, I will get, okay, no space, let me make it to the left a bit. Okay, so the last one over here, I want to differentiate, okay, maybe let me highlight so that you can see this 2 ln x, when I differentiate this, I will get this expression here. Okay, if I want to differentiate ln sine x, I will get this expression over here. Okay, 1 over sine x plus times cosine x. Then now the last one, okay, now minus away 1 over x plus 1. And I differentiate x plus 1, which will give me times 1. Okay, and then this will map to the last term over here. Okay, then this blue part here will give me these terms here. Yep. Okay, so therefore we simplify my terms from here. I will get 2 over x plus cosine x over sine x, then minus away 1 over x plus 1. Okay, And if you want to, you can simplify this to become 2 over x. Cosine x over sine x, I hope you remember this is cotangent x. Cotangent x minus 1 over x plus 1. Okay, and this is all for this worksheet. And now that you have learned how to differentiate logarithmic functions, you can now also try the practice questions under 2b, which is over here. Okay, this will mark the end of this